moving forward, what we need to do is, let me put some side comments over here. We understand that the aim is to solve for the fresh water over here, the volume of fresh water in here. So what is the feature? How do I solve that? Well, the most dynamical thing we know is once you remove the water, that it rises up. Well, why does it rise? It's due to buoyancy. Okay, so we identify that we want to look at buoyancy, and buoyancy is a type of force. And then now we have a standard way to deal with force. I will cover that a little bit more if you are not as familiar, or you start to forget the skills of how to deal with that, but I'll sort of go through it a little bit more rapidly and in more detail in the future. So you basically, anytime you hear the word force, you start with a free body diagram. The free body diagram should ask two questions. It should be asking, you draw a free body diagram for the object that you're interested in, and you should ask yourself, what is touching the object and what is not touching the object? If you ask these two questions, you'll guarantee to be correct, that you don't miss out any information. Because anything touching will give rise to a contact force, anything that's not touching it yet provides a force, give rise to, basically, you guessed it, non-contact forces. Okay, so we're interested in the ship rising, so let's draw a free body diagram for the ship. All free body diagram arrows should start from the middle, and let's ask what is touching, what is in contact with the ship. Well, first of all, it's in contact with the fresh water. That's good. And secondly, it's in contact with the seawater. Let's start with the seawater, and let me label this for clarity, sea and fresh. So in contact with the seawater, so what does the seawater do to the ship? Well, the seawater creates that buoyancy force that floats the ship. So it has a buoyancy force that's pointing up. Let me make it B for buoyancy. Okay. And then the second thing that it's in contact with is the fresh water. The fresh water is going to weigh it down, so it's going to have a weight from the fresh water. That's the force that the fresh water is going to exert onto the ship. Okay. Now you ask yourself, is there anything touching the ship? No. The answer is no, because it's only in contact with the fresh water inside and the seawater outside. Sure, it's in contact with air as well, but we probably don't need to consider that because there's no air resistance or friction that is important enough to be considered as a question. So you're done with all the contact forces. Then you also ask yourself, what is a non-contact force that's going to exert a force on a ship? Well, in our physics course, we only learned one non-contact force, which is gravity. So gravity will also create a weight for the ship. So that is your free body diagram for the ship on the left. So basically, you can immediately translate that to an equation like this. B has to equals to W fresh plus W ship. And the reason should be obvious, because all the upward forces should balance the lower forces if the ship were to float. Otherwise, it will either fly into the air or it will sink to the bottom. So this is in the equilibrium situation. While we're at it, let's do the second one for practice as well, now that you know what to do. So in the unloaded situation, so this is the ship, what is it in contact with? That's correct, the seawater. So the seawater, again, gives you a buoyancy force, and that's it. That's the only thing that is in contact with the second situation. So in the before and after diagram, in the after diagram, the only thing in contact with the ship is the seawater, which creates that buoyancy. So this is a buoyancy due to the sea. And then you ask yourself, is there a non-contact force relevant? Yes. So there is W ship, the weight of the ship is still there. Now, there was a second advice, is never repeat a variable that is not the same value. Okay. This is extremely important because it causes a lot of confusion. So let's examine what we have so far. My question is, what are the variables I've defined so far that repeats themselves, and are they the same? First thing that comes to mind is the B. Now the B on the left and the B on the right, you see that from your understanding of physics, you see that you understand that it's due to how much water is being displaced, or how much air of volume the ship has been sinked into the seawater. And clearly, the before and after is different. The after is much shallower, so the buoyancy force would be different. It will create a different buoyancy force from the before situation. So let me put a prime over there. The question is, do I need to put a prime for the weight of the ship as well? Now the weight of the ship doesn't change, so these two W ships are actually the same identical number, so we do not need extra prime to differentiate that two variables. So let me remove that. And as you can see, you can guess what this diagram translates to in terms of equation. It's basically B prime equals to W ship. Okay. All right, so this is the first step of solving anything to do with forces in the solve procedure. The next step is try to expand your equations. So now you go and expand everything, because over here I just have a very simple equation, but now we need to expand it in terms of variable that hopefully contains this refresh or something that leads to this refresh to allow me to solve it. Okay, so we know from our studies, we know the buoyancy force is rho vg, and then we have the freshwater weight is always mg plus mg. Now clearly the m's again is repeating, never repeat a variable, so let's actually distinguish them. It's sufficient now that I've written it once on top. I'll just put the first letter of it. It's much quicker that way, yet I still know what mass I am talking about. And on the left, now we can ask ourselves, what do we know? On the left, what is the rho? Well, the rho is, what is rho and what is the v? Because g is obvious. The v is the volume that is displaced or submerged, right? Submerged in where? The rho is about that fluid that is creating this buoyant force. In this case, it's the seawater. So I'm going to put C over there. Now, that's on the left, and on the right, we can repeat the same thing. This is rho Vg equals to W ship, so it's M ship G. Okay. Now, is the volume displaced in this case the same as before? No, so I need a prime over here. And is the density of the sea the same? Yeah, that's the same. Is the mass of the ship the same? That's the same. So every other variable over here is the same. It's really just the v prime that is different. The v prime is the amount of volume displaced over here. As you can see, it's shallower than the amount of water displaced over here when it is deeper. Okay, so now we can go forward and try to expand it a little bit more. Because we're given one more information over here, we want to try to use that. So we know that the volume displaced is the base area times the height, right? So we can have rho c and area times the height of g. So that gives me the volume of freshwater over here. Okay? That's the base area times the height, and that's the volume displaced, so I'm going to copy the rest plus msg, and over here I have rho c, but this time the volume displaced is the base area times this new height, g equals msg. Okay, now you see that my a has been repeated over here. Immediately I'm very alert of this, of never repeating a variable unless they are the same. So I need to ask, is the area the same over there? Of course, that's the base area of the ship, and it doesn't change when it rises a little bit out of the ocean. So that A is indeed the same. So now you have set up your equations, and now I want to take advantage of this information over here, h minus h prime. So this is a little bit of the specific trick that only works for this problem, not so much as a general trick, but I'm going to do that as well, is I see a h over here, I see h prime over here. I can take these equations and subtract them. So on the left, well, if I factorize out all the common factors as well, you'll see that it gives me this on the left-hand side of the equal sign if I subtract these two equations. And then on the right, I basically have this from the left-hand side subtracting this from this side. So basically, just to recap, on the left I'm doing this, subtract this, but every factor is the same except for the h, so that translates into this part. And then on the right I'm taking this, subtracting this. Okay. Now this is a good time where you mentally go in and tick off all the variables that you do know and which ones you don't. So first, this is usually given. The area, in fact, is precisely given. This is a nice, the way that I just subtracted this, I was basically inspired by what is given over here. I see a subtraction, so you can subtract. This is more like a specific math technique, not a general problem solving technique, but here we go. I actually do know this. G is another constant we are completely known. And finally, there's a nice thing over here as we see that there's a nice cancellation between the weight of the boat. Basically, the mass of the boat remains the same from before and after. So this actually cancels. And the only thing that is unknown is the mass of the fresh water. And this is also another nice thing you see by actually labeling your variables. You can immediately know what that variable refers to. Alright, so this immediately will result in you getting the mass of the fresh water known out of this equation, because it's one equation, one unknown. A little bit more explicitly, this is the time where you can plug in all the numbers. This is 2240, and this is 8.5, this is 9.81. In fact, as you can see, the g's actually all cancel out. But in principle, just to be very obvious over here, that is what you can do. And now that you've got your mass of the freshwater, sometimes this is where people get confused again. So that is the best, this is where this comes in with writing down your aim, because now you can go and ask yourself, well, I want the volume of the freshwater. How does this relate to the mass of the freshwater? Well, probably through density, because we know the equation or the definition of density is mass per unit volume. So let me put the variable I want. I want the, sorry, not C, I want the volume of the freshwater, which means I need the rho of the freshwater and the mass of the freshwater. Okay. And in fact, we've just solved this. This is given, which means the volume of the freshwater is the mass of the freshwater, which we have just solved over there, divided by the density of the freshwater. And you get your final answer. Now, the last comment that I made during today's session is about units. This is a wonderful question. I'll go through that with much more examples next week. But basically, the short answer to that is, if everything you used in the beginning is SI units, in fact SI base units, that means meters, kilograms, or seconds, or anything that make out of this MKS system. This is the SI base units. Then you don't need to keep track of your units. So this is a nice pro tip for you guys. It makes your equations much cleaner. For example, if you look over here, you don't have to copy so many units, maybe for several lines, and there's a lot of redundancy there. So if you start off with SI base units, the beauty of that is you will always end up with SI base units. So all you have to do is be familiar with what are SI base units. So what is the SI base unit for volume? Well, it's meters cube. So all you have to do is at the end just plug in meters cube, and you'll be guaranteed this is correct. So this is your final answer, whatever that number is, and add a meters cube. Okay, just to reiterate, if you start off with SI base units, you will end up with SI base units. Okay, so there's several parts that I've gone through over here. This is how you solve the problem. I believe the rest is really just plug and chug. So just to in a summary, just to summarize everything over here, you see that everything below in blue is let me write it in pink. Everything over here downwards is plug and chug. So if you finally get this equation in blue over here, then you can just plug in all the numbers. This is the process of plug and chug over here. But if you only know how to do plug and chug, you will miss out all of the above. This is what I call the setup. The setting up, as you can see, takes up much more of the work. Okay, so going forward, I'm going to focus a lot on how to set up so that really you can utilize the last bit of skills that we're so good at, which is plug and chug. Sometimes a lot of people discourage you saying never do plug and chug in physics. That's a little bit exaggerated because of course in the end you do plug in the numbers and you chug through the algebra to get your final answer, but not at the beginning, because if you don't know what to plug in, you will basically be completely left stuck in the beginning. So this plays a very big part in setting it up. So just a summary of what I've done over here. I have the setup actually consists of two parts. It's the bit in black, which works for every single problem, and the bit in orange and blue, which works for force problems. If you look at this, you might think that, okay, anything in blue and orange is much more important for solving the problem because it looks like this is what ultimately gets you to this. However, that is misleading because I can only do this if I had my diagram and aim and information put up over here. So, and in fact, I would really claim that the diagram aim step is much more important because it works for every single problem. And reiterating the importance of this is, with this system of knowing what to do to start off with, you'll never be left staring at a problem blank, not knowing what to do, because I would argue that everyone can do these two steps, step number 1 and step number 2. And I would argue that if you can do these two steps well, it will set you up for success for doing this last step, which gives you the final answer. Okay? All right. So in the future, we are basically going to do a lot of problems like this, and we're going to stare at a lot of these problems, look at how to translate it into a diagram like this, state your aim, and then I'll give you more specific tips on, for example, if it's a force problem, what is the procedure to do every time, and then you can do the favorite part yourself, which is chugging in the right numbers. So hopefully this is clearing up some of the confusion while I was doing this live, and also a good summary for everyone. All right, see you guys very soon.